Going to talk about hypothesis testing. This is another section of our inference. Last chapter, we did something called confidence intervals, where we got a point estimate and we added and subtracted a margin of error and we guessed where the population is. So confidence intervals is taking a point estimate, one point in time, making an interval and saying, hey, based on this sample, I think the population is between these two numbers. Whereas hypothesis testing takes a known population or what you think to be known and tests against it. So in confidence intervals, it's kind of like a blank slate, and you're using a sample to infer out to a population. You're saying, hey, I got this sample. This is what I think the population is. Where in hypothesis testing, we have a set like mean or a set proportion. And we're saying, hey, I know what this number is, but I think it's wrong. And we're going to test against it. Sometimes you're going to think it's less than, greater than, or maybe not even equal to it. We just think that it's wrong. So here you have a set parameter. Remember, parameter is a name for any population number. You have a set parameter. You think what it is already is, and you're going to test against it because you think it's something different. Okay, so your statistical hypothesis is your conjecture about that, saying, hey, it may or may not be true. The null hypothesis is what the population is right now or what people think it is. The population is always going to have an equals in it because that's what we think it's equal to now. So this is that there is no difference between what we are saying and what we think it is. All right. The alternative hypothesis is always going to be either that, hey, I think this number is going to be less than, greater than, or I'm not really sure, but I think that it has changed. So that's your first step in hypothesis testing, is coming up with what I call the ho and the ha. The null and the alternative hypothesis. The A is for the alternative, and null is like a little kind of a funky kind of zero for a null set. Okay, so ho and ha. Yeah, I know I call this ho. Just wait. Okay, so anyway, so first steps. There are 6 steps. So the ho and the ha is always going to be either, for this first section, we're going to do mean testing, a mu, remember that's our population mean, equals. It's always going to be equal to whatever number we think it is right now. Remember that is our this must always be termed in terms of the population. Then our ha could be a mu less than, it could be a greater than, or it could be a not equal to that number. So those are your first 2 steps. The next step is to draw a curve and shade. So we're going to talk about that next. We're going to draw a little normal curve, and this number right here is where the mean is going to be set. And we're either going to shade left, right, or both sides. So we either think that this mean is now less than, we shade left, greater than, we'll shade right, or two-tailed, we don't know, so we'll shade both. And we're going to shade these little tail areas, and I'll talk about that as we go along. Then the next thing from the chart, and you're either going to get this from the Z or T chart, you're going to find this critical value on the curve. Okay? And this is either going to come from a Z or a T, depending on what type of test you do. So the type of test you do determines what chart you are, and I always remember this from something that AP talks about, ZAP, TAM. Okay, Z's always use P, T's always use mean, and we call that ZAP, TAM. So the Z chart always uses proportions, and T's always use means. Okay, and then so we're going to practice doing just the first 3 steps first, and then we're going to go through and find the rest of them. Today we're going to compute a test statistic or a test value, and we'll talk about that when we come back. And then we're going to talk about 5 and 6, and we have a conclusion statement that we have to write. So let's practice on the first 3 steps first. Okay, so a medical researcher, we're going to state the ho and the ha And then we're going to draw the curve and shade it appropriately. So we're going to practice on these first two steps. A medical researcher is interested in finding out whether a new medication will have any undesirable side effects. The researcher is particularly concerned with the pulse rate of the patients who take the medication. Will the pulse rate increase, decrease, or remain unchanged? All right, so the mean pulse rate right now is 82 beats per minute for this group of people. So that means our mu right now is equal to 82. This is always a freebie point. It's always equal to a population number. Don't ever use any sample data here. Now, that means that this curve is centered at 82. Now we're going to give a group of people this medication, and we're worried about the pulse rate, a side effect of pulse rate, but we're not sure what's going to happen to the pulse rate. It can go down, up, or it may stay the same, but we don't really know. So if we don't know if we think it's going to go down or up, we just do what we call a two-tail test or a not equal to test, and we make it not equal to 82. Then if it's a not equal to, we're not sure if it's going to go down, so we shade the left tail, or up, we shade the right tail. And I'll get into why we shade those tails a little bit. But why did you shade both? Because we're not sure if it's going to go down or up. These tails are just approximately picking a point at right now and shading. That's all you need to worry about. All right, number 2, a chemist invents an additive to increase the life of an automobile battery. The mean lifetime of the auto battery is 36 months. Okay, so right now, the mean lifetime of an auto battery is 36 months, so mu equals 36. We think that if this chemist invents this additive, it's going to increase this 36 months. So our theory, our hypothesis, is that it's going to go greater than 36. So we're at 36 right now, and these numbers should always be in terms of the population, and we think it's going to be greater than. So since we think that this is going to increase, we shade the right tail. This is called a right tail test. This is called a two-tailed test. This is called a right tail test. Okay, third one. A contractor wishes to lower heating bills by using a type of insulation in houses. If the average monthly heating bills right now is 78, what would the hoe and the ha be? Okay, so mu equals right now 78 in this type of houses. He's going to add an insulation to lower the heating bills. Less than 78. We shade. This is 78 right here at the hoe, at the mean. This is our null and alternative once again, and it's a less than test, so we shade left. Just pick an area on that tail. It's called a less than or a left tail test. Okay, so take a minute, pause the video, and practice these two. And then unpause the video and check to see if your answers are right. Okay, so in the first one, they think that if we give expectant mothers a vitamin, the birth rate of babies will increase. So the average birth weight between this group of babies generally is around 8.6. So if we give them a vitamin, then it'll increase their weight. So increase was the key on that one. This one, we're not really sure, but we're going to try playing soft music during a test and see if it changes the results. In the past, the test score was 73. We're just going to see if it changes it. Maybe it lowers it, but the key on this one is change. We don't have a direction, so we just say not equal to and shade both areas. Okay, so that's step 1 and 2 in hypothesis testing. Now we're going to find where this shading starts. Okay, and each of these problems we're going to find where this shading starts. And that's called a critical value. We're using a critical value from a t-chart. Okay, so you need your t-charts out. So pause the video if you do not have your t-chart out. So remember, Z's always use P's. We're doing mean testing today. T's always use means. Okay, so we're here, T always means. So we're either going to get your t-chart out, we're going to do that, or I'm going to show some of you, if you have an 84, how to do this on the graphing calculator. Let me clear my annotations here. Okay, so got our t-charts out. Remember, on the t-chart, df is always n minus 1 for right now. So when you're looking up on a t-chart on here, you take your sample size minus 1. And now last chapter, we used it for confidence intervals, which were down here on the bottom row. But now we're going to look up here for this tail probability. So whatever this tail area is, that's the area we're going to look up for our t. All right, so let's talk about it. And then I'm going to also show you if you want to learn how to do it on the calculator. So let's ignore this calculator thing for just a second and talk about these critical values. Okay, I had talked about it a little bit before in the confidence interval section, but we're going to talk about an alpha level. The alpha level is just your shaded area, total shaded area. Okay, and it's this symbol here, and that is a Greek symbol, alpha. All right, and it's right here too, when typed. Okay, so we're going to do a left tail test for a sample size 20. So this is step 3. So we've already determined that it's a left tail, so that means it's a less than test. We're going to shade left, whatever the HO was we put right here, the null hypothesis, we put right there. And what this alpha level tells you is the total shaded area. So that area, total, is 10%. So that means this shaded area, which we call rejection or critical region, is 10%. All right, so I go to my t-chart. My sample size was 20, so that means my degrees of freedom is 19. So I'm going to go to my t, and I'm going to go down to 19. And then this area, I know it's a right tail test, but they're telling you the tail area. The alpha level, these are your alpha levels, total alpha. Okay, so this would be alpha is total area. Okay, we'll talk about when you have to divide in a minute. So we said it was 10% and 19. So our critical value is 1.328. So our critical value is 1.328, and we're on below the mean, so we're going to make it negative. Remember, T's and Z's are symmetrical, so if it was up here at 10%, we would make it positive. Okay. Next one, a right tail test for a sample of size 36. I'm going to go, let's do the chart first, and then I'll go back and show you how to do these on a calculator. Okay, so there was our HO. They said it was a right tail test. It was a greater than test. So we shade right. And they're telling us that this area right here is 5%. That's your shaded area, your alpha. All right, so the degrees of freedom was 30. The sample size was 36, so the degrees of freedom is 35. It's going to be closer to 40. I'm going to go with the one closer to 40 for this. So T distribution, I'm going to slide down. There is no 35, but the sample size was 36, so I'm going to go closer to 40 on this. And the alpha level was 5. So we go down, and our critical value is 1.684. So the alpha level they give you was 5. The sample size was 36. There's no 35 degrees of freedom, so we're going to go to the closest one. I have no idea what's going on with that. So 1.684, and it's a positive because it's a right tail test. All right, two-tail test. A two-tail test for a sample size of 17. That means our degrees of freedom, 16. Two-tail test, now watch, be careful with this. A two-tail test means that it was a not equal to. So we shaded both sides. Now watch this. Since it was a not equal to, we have to divide this alpha up. This is total shaded. This is total shaded. Divide this alpha up into two parts. That means this is going to be 2.5%, and this is going to be 2.5%. All right, let me go over that again. The alpha level is your total shaded area. When it's one tail, it's the whole thing. But if it's a two tail, you have to kind of divvy this up between the two. Okay, so then we go to the T-chart, degrees of freedom 16. And now we're doing 0.25. So right here, 16 and 0.25, 2.12. Positive and 2.12 negative. You just make it both positive and negative. So let's go over that again. When it's a two-tail test, you have to divvy up your alpha level onto both tails because this represents your total shaded area. Okay, last one. Two-tail test for a sample size of 50. That means your degrees of freedom is 49. Your alpha level is 0.01. It is a two-tail test again. So we need to shade both tails. That means it was a not equal to. The hoe would be right here. Degrees of 49, alpha 0.01. The total area is 0.01. So we have to divvy that up to 0.5% here and 0.5% here. We go to the T distribution. And we go, where am I? Right here. 0.5% here. And it was 49. So we're just going to use 50 right here. Mass, isn't it? So 0.5%, 2.678, 0.5%. So 2.678, 2.678. Okay, so now you have just completed the first 3 steps of hypothesis testing. You're going to go back up, and for those of you that have a TI-84, and it's only some of the TI-84s, it will find this critical value for you. I'm going to show you how to do it. So if you go back up here, and this is only for people, so you can check your calculator. If you have an 83, you do not have this. You're going to have to use the T-chart. So I'm going to show you a function that will replace the T-chart, so you don't have to use the T-chart. All right, this is only for 84 people, and this is only for, so if you have an 83, or if you don't have this function on the 84, the older versions and the older software do not have this. So for all of you, you can check. If you have an 84, you can check. Go to second bars and see if you have this function called inverse T. If you have this function, so it's going to be right here. So it's going to be second bars, and it's going to be inverse T. Looks like that. Okay, if you have it, you can use this function and it'll give you the critical value. If you just want to use your T-chart, that's okay with me. But on this one, I'm going to go to inverse T, and I'm going to show you in a second. And I want the area in the tail. The area in the tail is 10%. And then the degrees of freedom, 19. If you go to inverse T, the area in the tail is 10%. It's always the area in the left. Degrees of freedom is 19. And then it gives you that negative 1.38. it's a little bit, it's actually more accurate. It's doing a calc interval to 10 decimal places, so the calculator is a little more accurate than the paper and pencil. But negative 1.328, same thing that we got, negative 1.328. Okay, on this one, you're going to do inverse t. Now, the area in the tail is 5%. The way that this calculator reads it, it always reads area to the left. Right? So when you type in something, if you type in 10, it's reading this area here. Okay, so on this one, I want a right tail test. So if I put in the tail area, 0.05, and then the degrees of freedom of 35, it's thinking that I'm doing this area here. All right, so what's going to happen, instead of getting positive 1.68, I'm going to get a negative. Just change it to a positive. Or if you want to do it so that you get a positive, it's always the area to the left. If this is 5% and this is 95, and if you put in that, it'll give you the positive. And I'll show you both ways. So second bars, inverse t. I'm going to put in 5%, and then, oops, I forgot the degrees of freedom. Degrees of freedom, 35. Sorry, 35. Paste, and you will get a negative 1.6895. It always does, this is always the area to the left. But remember, they're symmetrical, so just change that to a positive. Or if you want to do it, it's going to be the same answer. You can do 0.9535, and it will give you the exact same digits, but just positive. Okay? So you can use either one, 1.68, and that theirs was a little more accurate, 1.689, I think it was on the calculator. And either is fine. Did I do that wrong? Oh, well, okay. Anyway, I may have slipped up on one of the things. All right, so the right tail, you can do 5% and look up 5% here and make it just positive when it comes out. Or you can do 0.9535 and it'll make it the positive, either one. All right, two-tailed. All right, so two-tailed, inverse t. Remember, the calculator isn't smart. You still have to tell it it's 0.025. So 0.025, comma, degrees of freedom is 16. Second bars, inverse t, 0.025, 16, paste, right, and I get negative 212, which is what we got when we did it by hand. Negative 212. All right, so what I did is this area, and now I needed both positive and negative because it's a TwoTail test, so I make one negative, make one positive. All right, last one. And if you don't want to use this function, you can always use your t-chart. That's fine. Not everybody has this function. I'm just showing you a little shortcut. All right, so degrees of freedom 49. It was 1%. We divided it into half. So 0.005. Last one, second bars, inverse t, 0.005, and 49. And we get negative 2.68, which is what we got, negative 2.68 here. I just rounded this one. So you get a negative and you need both, so you make a positive. Okay, so you can use your good old t-chart, which I did in blue, or if you have the 84, you can do this function if you wish. You have two choices. If you don't have this function, then you're going to have to use the chart. All right, so that is our first 3 steps. So I'm going to stop the video and pause it And we're going to do another video and call part 1 and part 2, just because for time's sake. So we have completed the hoe and the haw, the null, remember, and the alternative. We draw and shade our curve. We did that. We drew and shaded our curve, sorry. We found the critical value either from the chart or I gave you that function inverse t. Remember, t's are for means, z's are for proportions. And then when we come back to the second part 2 of the video, we're going to do a complete test and do sections 4, 5, and 6.